In today's lesson, we're going to be looking at trees and binary trees. So as a starter, think about how you would explain and describe the structure of a file directory system on a computer. Now sometimes data isn't actually suited to a linear structure. It might be hierarchical in nature. Think about a family tree. A family tree doesn't occur with one item after the other. It looks like a tree with branches. We can think of the directory structure in an operating system, or the file structure on a computer of an example of this. Like we did in linked lists, every item is known as a node. A node may have links to children and some to parents. Now we have looked previously at how arrays store data in blocks of memory. You can see the example on the right hand side. You can see we've got an array here and there's no room to grow in memory. Now trees are different. Like linked lists, each node of a tree will have a memory location. If it has children, like a linked list again, it will use pointers to other locations of memory where these nodes might be stored. So the data in a binary tree may or may not be next to each other. There are occasions when trees are actually better at storing non-hierarchical data too. And this is the case for what we call a binary tree. A binary tree, remember binary usually has two options. Well, in a binary tree, every node has at most 2 children. It can have 1 or it could have 0, but the maximum it can have is 2. When creating a binary tree, we have to think of the following rule. When we're entering a number, if it is lower than the last value, it goes to the left. Otherwise, it goes to the right. Here's an example using this type of tree. You can see the rule. As each number is entered, if it is lower than the last, it goes to the left. Otherwise, it goes to the right. Here's our array. You can see our first value is 6, so this goes at the start of our array. We then move to 4. Well, 4 is lower than 6, so it goes on the left-hand side. 1 is lower than 6 and lower than 4, so it goes on the left-hand side of the 4. 2 is lower than 6, lower than 4, but higher than 1, so this goes on the right-hand side of value 1. And we continue in this mode until we end up with the tree that is shown on the screen. So we need to think about why would we use a binary tree? Well, first of all, it takes a much shorter amount of time to actually search for a data value. If we're searching for a value 10 in the array shown on this screen, we're going to have to take 6 steps to find it using a linear search. But in a binary tree, it's only going to take 3 steps. Now look at this array. It's unordered. This means that we can use an unordered array to sort our values and to search them. Now remember, when we're searching a tree, if we think of the complexity of this tree, remember we're looking at big O notation, actually we're looking at a logarithmic. The reason it's logarithmic is because each time it's halving the data. It's going through and discarding almost half of the data. So we can think of this as an efficient way of storing and searching data. So now we've thought about how do we actually get items into a binary tree, we can think about reading items from a binary tree. And as we said before, it's quite efficient to search. To search through a tree, we call it a traversed or to read. And that's our key word here. So there are different ways that we can actually traverse trees. The first way we're going to think of is a breadth traversal. We always have a starting node, and in this example we're using P as our starting node. We then visit P's children. So P's children, we visit P, and the first one is F. So as you can see at the bottom, we've started to list out this algorithm. But it also has another child, S. So we represent this by P, then F, then S. So we visited the children and then the neighbours, and we return back to the next starting node. So the next node would be F. Now we've already got P, F and S in our array, so its children are B and H. But rather than moving down the tree, we move to its neighbour S, because S has children as well, which are R and Y. So we put these values into our array. Now we move to the next value in our array, which we've not seen if it's got any children, which is B, and it doesn't. So we move to H. H does have a child, so we add G into our array. Now remember, we're visiting the neighbours first, so we next go to R in the same level. R has no children, so we can move on to Y. Y has two children, T and Z, so we add these into our array. Now remember, we go back to the initial node. G has no children, so we can forget about that. T does have a child, so we add W, and Z doesn't. So we'll end up with our final array, which here is an algorithm for this. We have a procedure called breadth first traversal. We set our starting point to P. We start with an empty queue. You can then see our node in focus becomes our root. So that's a variable. Node in focus becomes our root, and root is pseudocode to say this is the start of the tree. We say while the node in focus is not null, it's going to display the node in focus, the data that it's got, and then it's going to use two functions called enqueue and dequeue. Remember, in pseudocode we can use enqueue and dequeue to put things into a queue or remove them from a queue. So we can look at the left and right children to the queue, then we can dequeue it, so take it out and move to the next item. The second type of traversal we can do is a depth traversal. And there are actually three ways of doing this: pre-order, in order, and post-order. In a pre-order tree traversal, we follow the rules root, left, right. So you can see here our root is P. We start with our root P, and then we move left. So F becomes our next value. We can still move at left, so we go to B and we write B. B doesn't have any children, so we trace the tree back to F and then go right. So we go to H next. H has a left, so we go to G. G doesn't have any children, so we travel back to H. H doesn't have any children, so we go back to F, back to P, and then we can start moving down the right hand side. So S, then R, Y, T, W, and Z. We can remember where we're going using a stack in this case. So we can remove an item off once we have completed visiting all that item's children. There's an example of a procedure shown here on the screen, or a function. This is in pseudocode. We've called it pre-order traversal. The node in focus is the node that we're currently looking at the moment. We output the node, then we check to see if there's anything to the left. If there's not, then we're going to move right. But if there is, if it's not equal to null, we turn that item into the node in focus. We've got a bit of recursion here, that we're keeping calling values until we need to unwind. And you can see the second section is right. Now the in-order traversal is also a depth-first traversal. We think of the rule as left, root, right. And a massive advantage of this one is it automatically sorts the data for you. You don't have to move any data in memory to sort it, and so you don't need any form of insertion sort. So here you can see the first value is our root, P. We then go down right to the bottom of the left-hand tree, so it becomes B next. Then we go to F, G, H. We can then move through the next section of our tree to the right-hand side of P. R comes next. Then we have S. Then we move down our tree, T, W, Y, and Z. One of the easy ways to do this is to draw around the outside of the tree. So you start at the top, you draw a line, and whenever you hit that node, at the bottom of the node you can draw a dot, and that is when you need to actually include that in the tree. The final type of depth-first traversal is post-order traversal. This can often be used to delete a binary tree. Our rule here is left, right, root. Now using my example, remember the top of our tree, the root of our tree is P. Now the easiest way to do this is to draw around the tree with a pencil, and every time you get to the right hand side of a node, include it in your answer. So the first item would be B. We then continue drawing around our tree, and the second one we come to is G, followed by H and then F. We continue drawing, and you see we've not reached the right hand side of P yet, so we carry on down the side and we'll meet R next, followed by W, T, Z, Y, S, and finally P. In a post-order traversal, the root node will usually be the last item that you visit. You can see the code here and the function that we created. It's very similar to the one that we've done before. We've got if node in focus.left does not equal null. We use our recursive function again to set the node in focus to the left. And we keep moving around, outputting our data. There's also a flow diagram here to show you how this works. So now we've got an understanding of the different types of traversals, let's have a little bit of a think of how and the need for these different types. Pre-order traversal is quite a common order. It's used often if we want to duplicate the data and create another identical tree. With this method, remember, the data is read root node first. So that means that we can't read any children until the parent is read first. So if we're recreating this tree, this is the option that we want to use. An in-order traversal is great if we want to search and sort the data values. We want to read it in order. Remember, there's no need here for a linear search or any kind of search here or sort. We can just traverse the tree in a certain way. We have lower numbers or items on the left and higher on the right. So we read them in this example in alphabetical order. And finally, our post-order transversal. If we want to delete data from the tree, due to the fact that, remember, every child in a binary tree depends on its parent, this method of reading a binary tree is good. Because if we want to actually delete data, we can use this method to never visit a parent before we've visited its children. This transversal method is also excellent for reverse Polish notation, a way that computers can deal with mathematical expressions. So to remove an item from a binary tree, it's slightly more complicated. The first thing we need to do is traverse the tree, find the node we want to delete. In this case, if we're trying to delete the node F, we save our value as node to delete in a variable in memory called node to delete. Now, because we start at the top of the tree, the root of our tree, our current node starts at P. Now, it doesn't really have a previous node, so we copy the value of current node into previous node. We then start to think about whether P, or whether the value we're trying to delete, F, is greater or larger than P. Now we know F is less than P, so we're going to go to the left of the tree. So we put our current node to F. Our algorithm will know that we found the node to delete. So our current node should say F, but the previous node is P. So when the item we find is actually a child or a leaf node, we can just delete the value. It's fairly simple. But we must set the left value of P to null. So when there's only one leaf child, so B from F, and we need to delete F, we can change the pointers. So we know that the pointer from P is going to go to B instead of F. Now we use the Hibbard deletion algorithm when there are two children. It is more complicated. And there are two rules to the Hibbard deletion algorithm. First of all, does it have a right node and does it have a left subtree? In the exam, you're not going to be asked to delete a value which has a left subtree. Let's have a look at an example. So to remove the node when we've got two children, we need to check the two rules. H is the right node from F. There's no sub-left tree from B, so all we need to do in this case is promote the right node from F, which is H.